In this section of Chapter 5, we're going to put what we know about chiral centers into our nomenclature. So for stereochemistry nomenclature, we're going to use the Kohn-Ingold Prelog convention in order to help put stereochemistry into our nomenclature. What this does is it assigns priorities to the substituents in a chiral center or around a double bond to help explain the arrangement of the stereochemistry. So first, let's look at chiral centers. We're going to label a chiral center as either being R, which stands for right-handed or rectus, or S, which stands for left-handed or sinister, is where the S comes from. So the label is going to go in front of the name. We're going to still name our compound as we have from our previous nomenclature chapters, but now we're going to put this stereocenter label in front of the name, followed by a dash. So if my stereocenter had an R in it, so I would name it as R dash, and then the name of my molecule as we have named molecules previously. So let's look at the rules on how we're going to assign R and S to our stereocenter. First, we're going to assign each group at the chiral center a priority. The higher the atomic number, the higher the priority. So iodine in our molecule would get the highest priority label, followed by bromine, chlorine, fluorine, then oxygen, nitrogen, carbon, and hydrogen. If there are any other atoms that we might see, such as sulfurs or phosphorus, we would just fill them in based on their atomic number. For isotopes, the higher the atomic weight, the higher the priority. So if we look at the three isotopes for hydrogen, tritium, deuterium, and hydrogen-1, tritium, H3, would get the highest priority, followed by deuterium, followed by hydrogen, with only a mass number of 1. If two identical atoms are attached to the chiral center, we have to look at the next atom on the chain. And we're going to keep going along the chain until we find a difference in the priorities, and we can label them as such. The key with this rule is that we are going to follow down the chain, one atom at a time. We are not going to jump to the end of the chain to look. So you want to make sure that you are walking down the chain one atom at a time until you find a difference. As soon as there is a difference, we label our priorities. So let's look at a couple of examples. So for my first example, we're going to have our chiral center. Around my chiral center, I am going to have a hydrogen, a deuterium, a chlorine, and a bromine. Deuterium is oftentimes labeled as a D in a structure. So there's no atom with a symbol of D, so we use that capital D to represent deuterium, a very specific isotope of hydrogen. So now if I'm going to look at this structure, I'm going to assign all of my priorities. So the top priority is going to go to the highest atomic number, which is bromine, so I'm going to label that as a 1. Following that, based on atomic number, is going to be chlorine, which I'll label as priority number 2. The two hydrogens there, hydrogen and deuterium, they're both the same atomic number. So now I have to base them on atomic weight since they are isotopes of each other. So deuterium would get priority number 3 and hydrogen would get priority number 4, or the lowest priority on our chiral center. So let's look at a slightly different structure. So I'm still going to focus on that carbon atom in the center as being my chiral center. From here, I'm just going to alter some branches around the chiral center. So I have a hydrogen, a CH3, an ethyl group, CH2CH3, and then a CH2Cl. So now I need to define my chiral center in terms of all the priorities. So we know right away that hydrogen has to be the lowest priority. So I can go ahead and label that as 4. Now I have to determine all the rest of my priorities. But you'll notice that all the rest of them are carbon attachments. I have a CH2Cl, a CH2CH3, and a CH3. So that means I have to walk out one more carbon on each, or one more atom on each of those branches until I find a difference. So if we look at the CH3, it is connected to 3 hydrogen atoms. If I look at the CH2CH3, that carbon is connected to 2 hydrogen atoms and 1 carbon atom. If I look at the CH2Cl, this is attached to 2 hydrogen atoms and 1 Cl. So based on that alone, I should be able to determine priorities because there are differences there. So now I see a difference with the 3 hydrogens. So that is going to get priority number 3, the next lowest. The carbon atom on the bottom has 2 hydrogens and a carbon. The other one has 2 hydrogens and a chlorine. Chlorine gets higher priority than carbon, so the one on the bottom would be priority number 2, and the one on the left would be priority number 1. Again, because of that chlorine-carbon difference. So I'm going to look at one more structure and see if we can determine all of our priorities based on all of the rules we have learned thus far. So here's our entire structure. What I would encourage you to do is pause the video and see if you can determine how many chiral centers this structure has. And then for each chiral center, see if you can determine the priorities around it. So if we look at this structure only has one chiral center. The other carbon is not a chiral center because it would have had 2 CH3s associated with it. So we're only going to be looking at one chiral center here. So now I want to be able to assign my priorities. Hydrogen always gets priority number 4. But then once again, if we look at the next attachment to all of the attachments, they're all carbon atoms. CH2, CH2Br, CH3, C, CH3, CH3, Cl. So we need to figure out which one we're going to look at in terms of priorities based on the next atom that it's attached to. So if I look at the carbon on the right, it is attached to 2 carbon atoms and 1 chlorine atom. If I look at the carbon down at the bottom, it is attached to 3 hydrogens. If I look at the carbon on the left, it is attached to 2 hydrogens and 1 carbon. So based off of those attachments alone, I can look and I can see that there are differences with them. So the carbon at the bottom, the CH3, is going to be priority number 3 because it only has hydrogens attached to it. The one on the left is going to be priority number 2 because it has 2 hydrogens and 1 chlorine. The carbon there on the right-hand side is going to be priority number 1 because it has 2 carbons and 1 chlorine atom. So you'll notice that even though there was a bromine in this structure, it does not play a role in any of my priorities because I did not need to walk far enough along the chain in order to get to the bromine atom to cause it to be a difference. So this is where you have to walk out one atom along the chain at a time until you find a difference. As soon as there's a difference, we label our priorities. So if we have multiple bonded atoms within our structure, those atoms are going to be equivalent to the same number of singly bonded atoms. So here's what I mean by this terminology. If we have a carbon-carbon double bond within my chain, I'm going to treat it as if that carbon atom was attached to 2 other carbon atoms along that chain. So instead of thinking of it as a double bond, we're going to think about it as it's being bound to 1 carbon atom and then another carbon atom. So basically we count that carbon atom twice. So if we look at this in the context of a structure, in order to determine our different priorities, this is what it would look like. I know bromine's going to get priority number 1, and I know hydrogen's going to get priority number 4. The other 2 attachments both start with hydrogen. So now I have to start looking at the counts that I have. So the one on the right, that carbon atom, is attached to 1 hydrogen, but 2 other carbon atoms because of the double bond. So remember, I'm going to count each one of those double bonds individually for priority's sake only. The carbon atom down at the bottom is attached to 2 hydrogens and only 1 carbon atom. So now I can see that there is a difference. So the carbon atom on the right is going to get priority number 2 because it's attached to 2 carbons and 1 hydrogen. The carbon at the bottom is going to get priority number 3 because it attached to only 1 carbon and 2 hydrogens. Another way that we can look at this is they don't just have to be carbon atoms. We can look at this in terms of that carbonyl functionality. So if this shows up along my chain, I would think of this as being attached to 2 oxygen atoms. And I would count that oxygen atom twice because of the double bond. If we are dealing with a triple bond within the structure, I would treat this carbon as if it were bound to 3 other carbon atoms. I would treat that triple bond as 3 carbon atoms in terms of my priority. We may see the same thing with our nitrogen. So if we have that cyano group in our structure where we have the carbon triply bound to the nitrogen, I would end up, for my priority's sake, I would end up saying that that carbon atom is bound to 3 nitrogens because of the triple bond when I'm counting for priority only. So let's look at one more example in terms of what we're going to be able to assign our priorities to. So again, take a moment, pause the video, and see if you can assign all the priorities in this structure. So to assign our priorities, we know that that hydrogen is going to get priority number 4, our lowest priority. The highest priority is going to go to the oxygen that is directly attached to our chiral center. So the other 2, we now have both carbon attachments. So the carbon at the top is attached to 1 hydrogen, and it is attached to 2 oxygen atoms because of the double bond. So remember, we count each one of those bonds as 1 attachment to an oxygen. The carbon at the bottom is attached to 2 hydrogens and only 1 oxygen atom. So once again, we see a difference. We can assign priorities. The carbon at the top is going to get priority number 1 because of the 1 hydrogen and the 2 oxygens. The carbon atom at the bottom is going to get priority number 3 because of the 2 hydrogens and only the 1 oxygen. Now, after we have labeled all of our priorities, we're now going to view the structure in 3 dimensions with the lowest priority pointing back. And that is going to be the key to this, is now we have to take that structure and we have to put it in 3-dimensionality. So remember, sp3 hybridized centers. And we're going to take priority number 4 and we are going to point it back behind the plane of the screen. I'm then going to focus on the other 3 priorities. And if those other 3 priorities are in a clockwise numbering order, so 1, 2, 3 around the chiral center, we label that designation as the R chiral center. If we have a counterclockwise 3, 2, 1, I'm then going to label that stereocenter as the S stereocenter. So let's look at a couple of examples, and I'm going to go back to that 2-chlorobutane that we looked at in the previous chapter. So this was our structure for 2-chlorobutane, where the chlorine was pointing out in front of the screen. So I've already got this in 3-dimensionality, and I can assign my priorities. Hydrogen gets priority number 4, chlorine will get priority number 1. The CH2, CH3 gets priority number 2, and the CH3 unit gets priority number 3. So in this structure, the 4 is already pointing back. So it's already in the dashed line. The 4 is already pointing back. I do not need to do any rotation. That will not always be the case, so you will want to be very, very careful to make sure that the molecule that you are looking at, you rotate it in space so that 4 is pointing back before you look at the other 3 numbers. So since 4 is pointing back, I can now do my count. I have 1 to 2 to 3, and they are in a counterclockwise fashion. So 1, 2, 3 in a nice counterclockwise fashion. So this is my S stereocenter. So the full name for this molecule would be S2-chlorobutane. So again, we put that stereocenter in front of the entire name, followed by a dash, and then the rest of the name. So let's look at the enantiomer of this structure. So remember, this was the mirror image of this structure. So in our mirror image, priorities do not change. We still have priority number 1, for chlorine, priority number 4 for hydrogen. The methyl is a priority number 3. The ethyl group is a priority number 2. So nothing changes there. 4 is still pointing back in our mirror image, so we don't have to worry about making 4 point back. Once again, it already is. So now I'm going to pay attention to my 1, 2, and 3. Starting with my 1 up to 1, 2, and 3. You will see now that they are in a clockwise numbering order. As I go from 1 to 2 to 3, it is in a clockwise fashion. So this is my R designation. So the way that I would name this structure is it's going to be R2-chlorobutane. So one of the things that you want to notice is that enantiomers have different chiral center labels. If one enantiomer is labeled as S, the other enantiomer will be labeled as R. They will always have opposite designations. So here are 3 examples. I would recommend pausing them and see if you can name them with correct stereochemistry. So for the first one, this is 3-bromohexane. With our 3-bromohexane, there is a stereocenter shown. So I do need to make sure that I go through and I label all of my priorities. So bromine will get priority number 1. The longer of the carbon chains will get priority number 2. The shorter will get priority number 3. And then don't forget that there is a hydrogen pointing back that is priority number 4. Once again, hydrogen is already pointing back, so we just need to focus on the 1, 2, and 3. They are in a counterclockwise fashion, so this would be an S stereocenter. So the name for this would be S, 3-bromohexane. For the second structure, it is a 3-methyl pentane. And even though that methyl group is pointing out, there is no stereochemistry associated with this structure. This is an achiral molecule because there is not a chiral center. If you try to label your priorities, you'll notice that the 2 ethyl groups are the same on that carbon atom attached to the methyl group, carbon atom number 3. So this is not a chiral center because it's an achiral molecule. So there should be no R or S designation associated with it. It should just be labeled as 3-methyl pentane. The last structure that we have, it is a 2,3-dimethyl pentane. So if you'll notice with this one, because we have added in that extra methyl group, it does now give us a chiral center. We do have one chiral center. It is carbon atom number 3 because it has 4 different things attached to it. If you do your labelings for priority, the highest priority is the carbon chain on the left because that first carbon is attached to 2 other carbon atoms. The carbon on the right gets priority number 2. The methyl group gets priority number 3. And then don't forget there's already a hydrogen pointing back that gets priority number 4. So once again, since priority number 4 is already pointing back, we can do our count of 1, 2, and 3. It is in a nice clockwise fashion, so this would be an R, 2,3-dimethyl pentane. So molecules can have more than one stereocenter, so we have to be able to name those as well. And when molecules have more than one stereocenter, we will have multiple R and S designations within our name. Each of them is going to be found before the name with a locant, and we're going to put them in parentheses. So if I have a stereocenter on carbon atom number 2 and one on carbon atom number 3, I would have both of them out front, and I would just put them in numerical order. So it'd be something like 2R, 3S, dash, and then the rest of the name. So all of them go out front with the locant to tell you which stereocenter is which designation. So let's look at an example. So for this example, we have 2 different stereocenters. We have a stereocenter on carbon atom number 2. We have a stereocenter on carbon atom number 3 as well. So I would have to go through and assign priorities to each one of them separately. So for carbon atom number 2 with the bromine on it, the bromine would get priority number 1. The carbon with the chlorine would get priority number 2. The methyl group would get priority number 3. And then we have a hydrogen that is pointing out at you that would get priority number 4. So we do have a problem here. The 4 priority is pointing out at you. So before I can do my determination for R and S, I have to flip this molecule so that hydrogen is pointing back. Because of the flip of that molecule, this designation becomes an S designation. So please don't forget, before you can do the clockwise or counterclockwise, priority number 4 needs to be pointing back. So in this molecule, I would have to flip this structure so that 4 points back before assigning the R&S designation for carbon atom number 2. So now let's look at carbon atom number 3. My priorities for carbon atom number 3, chlorine gets priority number 1. The carbon with the bromine gets priority number 2. The methyl group will get priority number 3. And then we have a hydrogen pointing back that gets priority number 4. Since the hydrogen is already pointing back, I can just look at my 1, 2, 3 designation. So carbon atom number 3 has an R designation. So the full name for this structure would become 2S, 3R, and then 2-bromo, 3-chloro, butane. So you'll notice I have used the locants twice. I have used the locants once to tell you about the stereochemistry, and then I have used the same locants again, 2 and 3, to tell you about the substituents. If we have stereocenters on a ring, we are still going to start using R and S designation even within a ring itself. So in a ring, if we have carbon atoms that have 4 different things attached to it, we will use R and S designation to tell you about the stereochemistry. For di-substituted rings, we can use cis-trans designation if it is an achiral compound, meaning it is a meso compound, that even though it contains chiral centers, its mirror image is superimposable. Remember, it has that plane of symmetry in it. So if we have a meso compound, we can go back and use that cis-trans designation, but we're only allowed to use cis and trans if it is an achiral compound when it comes to our IUPAC nomenclature. So let's look at a couple of examples. So for our first one, we have 2 bromine atoms attached. They are both pointing out of the screen, so they are on the same face for us. So if I label these as carbon atoms 1 and 2, you'll hopefully recognize that they are both chiral centers from our previous talking about chiral centers in our previous chapter. So I can go through and I can do designation on chiral center number 1. So bromine gets priority number 1. The carbon with the bromine will get priority number 2. The CH2 unit will get priority number 3. And the hydrogen that is pointing back will get priority number 4. The hydrogen is already pointing back, so with this designation, the 1 position would be an R position. I could then look at the second carbon atom. So carbon atom number 2 is a chiral center. For that chiral center, once again, the bromine gets priority number 2. The carbon with the bromine, or 1, the carbon with the bromine would get priority number 2. The CH2 would get priority number 3. And again, I've got a hydrogen pointing back that gets priority number 4. So this designation would be an S designation because of the counterclockwise rotation of the 1, 2, 3. So a way that I could name this structure would be 1R, 2S, 1, 2, dibromo, cyclohexane. But with this structure, hopefully you also recognize that this was one of our meso structures. It is actually achiral. If I numbered it the opposite direction, this would be a 1s2r, 1,2-dibromocyclohexane, and it would still be identical to this structure. So another way that we could actually name this is we could name this as cis 1,2-dibromocyclohexane. Because it is a meso compound, we can use that cis-trans terminology in place of the RS terminology. But if we look at our structure down below, notice now one bromine is pointing out, one bromine is pointing back. So if we go through and you actually assign all of your designations, and I encourage you to try assigning all of your designations to make sure you get the same name, the name for this would be 1R, 2R, 1,2-dibromocyclohexane. And that is the only way we can name this structure. We have lost that plane of symmetry within our structure. It is no longer a meso compound. So we can only name this as 1R, 2R, 1,2-dibromocyclohexane.